So the NT architecture is a little bit different than maybe any other operating system architecture that I'm familiar with. But the features, the aspects of it are actually fairly familiar to people, and it causes some confusion. So let me explain what that means. Now, when we started doing, and Cutler and the original team started working on NT, it wasn't really clear what apps would be looking at. And in fact, the original notion was that they'd be looking at something that was kind of like OS2, because back in 87, 89, that time frame, starting in 89, we actually thought the next great operating system was this joint collaboration between IBM and Microsoft called OS2. And NT came along, and NT, by the way, is kind of it has two meanings. Okay, the way it was originally explained was as new technology, which indeed it was for Microsoft particularly, and the other thing was it stood for N10, or which was really written like that. And this was what Intel later called the i860. It was a processor that at one point they thought would be a successor to the 286, that whole family. Intel's tried to replace the x86 many times, but this poor orphan microprocessor actually gets lots of love and has been very successful. They tried to replace it with the beginning of the 80s with their ADA processor, the i432, the i860, and now they're making more progress this time replacing it with the IA64. Okay, but in 1989, we thought this would be a winner. As it was, it didn't work out that way. The MIPS chip came along, the Alpha from Digital came along, and then the PowerPC, which was a RISC-style chip. And so, in addition, of course, the i386. At the point we released NT4, we ran on all these processors, which was another big difference from Windows 9X. The interesting part is that the marketplace voted resoundingly for this processor, and by the time we got to Windows XP, I think these others pretty much had dropped off the map. But the system was built to be very flexible, very powerful, able to work to a bunch of different processors, and that's where the, I'll draw a piece way down here at the bottom, the HAL, and this is the hardware. One of the problems with mnemonics is you sometimes forget what they actually stand for.
Instruction layer.
Adaptation layer.
Oh, really?
I think so. But who knows? There's a project in my team called ALPC, which is actually technology going into Longhorn, which I think we've talked about, the PC and stuff. And LPC is the basic communication protocol for client-server on the local machine. And I thought the A stood for advanced, the project in my team. Turns out it stands for asynchronous. So that's the problem with acronyms. You say them all the time, you forget what they mean. So the HAL is down at the bottom. And this was the thing that would allow us to talk not just to, say, the MIPS versus the x86, but it turns out there's a whole bunch of other differences in computers today. And these are things like whether or not you're a multiprocessor or a uniprocessor, because there's some differences that take place there. Whether or not your BIOS is based on ACPI or some other protocol, say like the APM, the Intel Power extensions that didn't succeed all that well. Okay, that might require different logic within the HAL to adapt you to these differences. Today, the biggest HAL work is probably on very high-end machines. So these are high-end, maybe 64-way computers and stuff. They start to have a lot more kinds of speciality that's in the hardware that is dealt with by the HAL. So up here, we have a layer above NT, and this is basically the personality layer. Now this led to some confusion, which you can even see in some of the books that we've reviewed and published about NT, which was the notion that NT was a microkernel. Okay, and the reason people would think it was a microkernel, and we're not against microkernels. In fact, we hired one of the guys who was most successful with microkernels to run research at Microsoft, which was Rick Rashid. But the microkernel idea, actually, I'll draw this a little bit differently. The personalities were kind of like this. You had the kernel, which has the HAL down underneath, and so this is the NT kernel. And then you had some user mode, what we call them subsystems. And these basically gave you your OS personality, which is the same thing that happened in the Mach system, where this was like the microkernel, and this was the OS server process. And so you could run, in the Mach world, you might have a BSD server, you'd have a Mach native server, you could build other kinds of operating systems. For us, the world consisted of 3 subsystems. There was the OS2 subsystem. I had the privilege of removing that, I think, before we shipped XP. I personally removed OS2. OS2 came to be a really nice operating system way too late for it to succeed in the market. IBM actually did ultimately some really good work on OS2. So, but it did go away, and so we removed the compatibility with OS2 from the system. One that was more important, has a more interesting history, which is Posix. Posix came out of the Unix belief that if you built standards, you would be able to have applications write once, run anywhere. That sounds familiar for some reason. And it turned out to not be true for the same reason the other guy who's been saying that in the last 10 years has been wrong about it, that little latent bugs get exposed by differences in implementation, that we just are not good enough in software engineering to write the kinds of contracts between the implementer of an operating system service and the client of that service or the application program so that you can actually get write once, run anywhere. Excuse me. One of the problems is versioning. Now, and we have this problem all the time within our system, which is say that we release what we call Win2K for shorthand, but Windows 2000. And then we release XP. And we're going to release Windows Server 2003 SP1. You know, it's like I think the next thing that's going to come out the door. Longhorn is coming down the road. And our customers want their applications to run across all these platforms. And yet these platforms are improving in terms of security fixes, in terms of new features, new functionality, new capabilities. And you start to have this kind of versioning problem, which is you worked really well with one particular version of the system and you tested all the bugs out, but another version comes along and things are slightly different underneath and it doesn't quite work. Well, this is if you actually have the code and you can go test it. When you're talking about a standard like Posix, it gets even harder to be able to do that. The Unix community, Larry Wall did a great job in the Unix community with something called configure. And what configure would do is it would go through, it knew all the anomalies just by brute force, and Unix is a pretty simple system, really. It would go through and figure out all the different kinds of dependencies you could have gotten wrong, hack up your source, fix a bunch of stuff for you, so you pretty much could compile across a whole range of different Unix boxes. That was far more effective, I think, in my opinion, than the Posix standard was in producing compatibility. But what the bottom line ends up being is you're compatible with a particular operating system because you were compiled and you ran on that operating system. And we have not been able to really achieve better compatibility than running on the same code. This is just an aside. This is why the PC is so incredibly successful. I talked about that ecosystem and finally figuring out Microsoft's business. Microsoft creates this layer across the system called Windows. Price of Windows hasn't changed all that much, particularly for clients in history. Home, I think, costs the same as Windows 98 or 95 in the retail market, something like that. But underneath us, huge change. The PC hardware has evolved tremendously. ACPI, APM, ISA, PCI, PCI Express coming, USB, FireWire, all the different manufacturers who fight it out. And I'll tell you something funny, is that when I first got here, one of my friends who loves the Macintosh was talking to me about, oh, you're working for, and this is before we started putting Office on. The Mac guys love us now because they have Office on their platform. But, oh, you're working for them, I love Macs, I said to him, I said, if you love the Macintosh, you should be really grateful to Bill Gates. And the guy's like, what are you talking about? I said, the reason the Macintosh is a lot less expensive than it used to be is because of the pressure from the PC in terms of price has driven the cost. So even if you love the Macintosh, you're better off because the PC industry has competed against the Macintosh and driven the price down. And the source of that competition for us is we collect for Windows here in our business model, Microsoft's business model widely known, high volume, low cost product with great functionality for our customers. The PC business has been driving down in price, increasing in functionality, just absolutely dramatically because the competition that's taken place there. And yet, you can go buy applications, and when's the last time you bought an application and said to yourself, I wonder if this will work on my Dell computer versus my Gateway computer, my Toshiba? It doesn't come up very often anymore. And that is what's so amazing about what Windows has accomplished. We still have to work on this versioning a little bit because you may wonder, gee, I bought that application when I was running XP. Will it work when I run Longhorn? And we do a lot of work to try and make that true. But this is the amazing thing about the PC business. And so Posix has not been as successful as I think people who came up with it originally thought. And I know some of the guys who are on the committee, and hopefully they won't be too mad at me for saying that. There's also the problem that a lot of our customers weren't that interested in Posix, but we bought a company a few years ago and now have a new version, which is called Interx, and it's really now renamed to be part of services for Unix. And this actually has increased the compatibility and stuff we had, because instead of just trying to be true to the Posix standard, I still have the old Posix books on my bookshelf from when we used to do that work directly. These guys were passionate about being sure that all the same tools and software, the GNU utilities, various things that people in that community were using on top of Unix were able to run well on Interx. And so this was the second subsystem that was very important to us. And then there was this other system that came along around the time of, say, 1992, 1993, which is what later became Windows 95, and this is the 132 API set. The NT system, so this was, the NT system started its design in about 1989, and this stuff all happened much later. Yet because we had this subsystem model for the OS personalities, we were able to support all three applications written all three of these models on the same NT system. And that led a lot to this architecture, which people thought was a microkernel architecture because it had the subsystems for personalities. Okay, so there's another part I'll tell you about before we launch into the architecture, what's inside this box, which is the NT core system doesn't just consist of the kernel. In fact, the service control manager, which is another very interesting topic, is based on letting people extend the system by building services, which are just user mode applications that talk to a component, which is the service control manager. And this is how people often extend the system. Now, where this kind of comes from is the following idea. If I log onto the system fires up some processes for me, most importantly Explore, which forms the desktop and the shell and everything, so I can then do operations and launch applications and stuff. And those applications generally persist as long as I have a login session, which is one of the cool things about terminal services, in that login session may exist long after I've signed off, gone home, signed on again. But those applications are still confined to that logon session. Suppose I want to have applications that are not confined to the logon session, but run all the time. In fact, I want to extend the Windows operating system to have some new set of services that run. But I don't like, oh, I'm going to log off and go home, and bang, the service goes down. And so that's what services are. They're basically extensions of the system, facilities that run, and these are pretty well known. There's SQL, runs as a service. Exchange, runs as a service. There are lots of applications like this. The ones that we sell in back office, like the IIS, this is like a service that runs. You configure your system, you start up the service, and now people are able to get functionality. Some of it's locally off the same machine, some of it's across the network. This is the services architecture. Now the services architecture uses RPC, which is a standard protocol, and I'll mention LPC in a few minutes, which is our transport implementation for RPC. Okay, so that's services. Now let's talk about the hardware adaptation layer, and just think of this as a set of routines that the kernel proper calls to control things that are specific to MP versus UP decisions, to talking to the different buses controlling different things about the actual lowest level configuration of the system. And so I don't think we need to say much more about that today. Instead, we'll focus on the kernel. So at the top, outside the kernel, and we'll focus on the 132 layer. The 132 layer is basically a set of libraries, and it's a subsystem process which happens to be called, for reasons nobody can explain to me, the CSR subsystem. Okay? And this is a process, and these are libraries, and this talks to, this is the user mode boundary I drew before, and the kernel boundary. Here's actually another layer I'll draw here, which is an interesting layer, which is the system library. And Unix has a similar thing. Or on your disk, you'll see it called ntdll.dll, which is a redundant name if ever I saw it. So the 132 layers, your application sits up here, links to the libraries, which talk to the kernel. And in fact, if you want to talk to the subsystem process, the way you do it is you loop through the kernel, and this is what LPC is for. It's a lightweight procedure call mechanism, so that I can invoke code over in the subsystem to perform functions that I want. So one piece of history is that, I think it was at NT4, that we actually took some of the functionality that used to be over here for graphics, and we moved that down into the kernel, into a driver, not the kernel itself, but a driver that runs in the kernel, called 132k.sys. And there's still some debate about whether we necessarily got enough of a performance improvement and stuff by doing this. But it became clear to us by the middle of the 90s that Win32 was the winner. That OS2 was becoming less important to our customers, that Posix had never really caught on as an application platform. And so we started to do tighter integration of the Win32 APIs into the system. Now, there's an interesting thing that happened, though, is the programming interface is up here at Win32. Mm-hmm. The NT interface, and these APIs that you call at this level, often the names begin NT, like there's an NT read file. And up here, there's a read file. And that's a Win32 API. But this is the native APIs. Now, what it means for something to be a system call or a kernel call versus a library function is just good to have a clear picture of what that is. Before we talked about the virtualization of hardware, and we use the example of processors and virtualizing them so you wouldn't have to call some guy on the phone to come in and use the machine because you couldn't both use it at the same time. We virtualized it into processes you could share at the same time. But operating systems also serve another important function which comes, it's kind of subsidiary, corollary of that, which is if I have multiple users working on the system at the same time, I have to keep their states separate so they don't interfere with one another. And so, in the most fundamental sense, one of the decisions about whether code executes up here or down in the kernel itself has to do with whether or not there are data structures that have to be protected. Protected meaning I can't let two different applications modify that data structure directly. So instead I encapsulate it by putting it in the kernel, give you a set of entry points into kernel routines, which then know how to modify the data structure safely so it is only in the permissible states. Okay, so it's this data hiding that really gives rise to the kernels. But I'll point out one thing just to harken back to my own thesis work. These services up here, or the subsystems like CSRSS, they're able to accomplish the same thing. Because they can have data structures inside, and the only way to operate in those data structures is to do remote procedure call invocation, which is similar to a system call. The problem is that, particularly on architectures like the x86, it's fairly expensive to cross in the kernel, even more expensive to switch to a different process, and then invoke something in that process. And so one of the trade-offs about building a system is the performance is better in the kernel than it is if you build it in services or in the system. And in fact, this causes some people, in terms of how they extend the Windows system, part of that vibrant ecosystem, the ability to extend it, is you can make a decision about whether to implement something as a service or as a driver, because a driver will operate directly in the kernel, and it's more efficient to access it. So we're actually trying to do the following thing moving forward, and we're doing this in certain areas of the system, which is get functionality that doesn't need the performance of being in the kernel to move out. So if there's a bug in it or a problem, because a lot of the stuff is from third parties, a lot of it's stuff that we don't actually see and we can't test. Some of it, there are bugs in our code too, of course. If it crashes out here in a service, you lost the service, you don't have a blue screen. Okay? And so we're getting people to do that. At the same time, there's certain things that are very critical that people like to have operate down inside the kernel, and they will continue to be there. Things that actually, real drivers that talk to your disk. You need to respond quickly in real time to changes in the hardware, changes in the bus. Things that might be involved in very high-speed video, actually controlling, interacting with the graphical processing unit on the high-end video cards. Well, actually, low-end video cards have those today. Okay, so those kinds of things make this decision about whether I'm in the kernel or whether I'm out in a service. Okay, so now, as promised, we will go focus on what happens in the structure of the kernel itself. And now we're looking at these NT APIs, which are the internal APIs of Windows. And the reason they're internal is because people normally don't program to these APIs, they program to Win32. And until Windows XP, we had a vested interest in people not programming to those APIs because we wanted applications to be able to work on an API set that was available on all our platforms, Windows 98 as well as NT. And that API set was the Win32. Today, we still don't publish the NT APIs, although there's a lot of information on them, and we share a lot of information about them, because almost all the functionality available to them is available through Win32. And in fact, we make Office and everybody else, we insist as much as we can that they program only to these Win32 APIs, but also because we think the future is in the direction of the .NET framework, which is a different API set, which is the one that ultimately will supplant Win32. And so that's the direction that we're going and the direction our customers want us to go, because that's where we're going to get the productivity increase as they write their own programs, their line of business apps, applications that run on top of Windows. So this is why these continue to be the internal APIs. There is, down at the bottom, the kernel of the kernel.
Kernel of the kernel.
The kernel of the kernel, just to create a little bit of confusion. And we had the HAL down underneath this before. Now what the kernel of the kernel does almost more than anything else is we can just regard it as a scheduler. This is actually the stuff that Dave Cutler himself works on most. He works on all sorts of parts of the system, but he's put a lot of effort in recent years onto the scheduler. Above that, we have a lot of different kinds of capabilities, which I'm going to draw in one form now for this diagram and another form later. We call it MM. This is the memory manager. This is the thing that implements virtual memory and a whole rich set of functionality associated with memory management. There's the I/O manager. The I/O manager controls a highly asynchronous form of doing I/O, which is one, we talked about multiple threads and being able to do those I/O operations in parallel. That's asynchronous I/O, which is something that has always been much stronger and more effective in NT than Unix. Unix introduced asynchronous I/O for the first time 20 years ago, but really only in the context of network operations. Because the problem with the network operation is you have to have a thread that sits there and kind of says, I got to wait for I/O to occur. There's another unifying service which it serves all the other services, which is the object manager, or we call it OB. Okay. I mentioned the LPC, the lightweight procedure call mechanism. This is how we use to communicate between user mode and kernel mode, between services, and we build RPC on top of it. So internally, between the internal services, we often program directly in LPC, like to talk to the CSRSS, the subsystem process for Win32. So drivers will use that because there's no RPC from kernel mode in the current system out to user mode. But almost everything else, applications that we write, middleware that sits on top, it uses RPC, which is a user mode mechanism which can be implemented in terms of LPC on the same machine. It can use named pipes. You can use TCP, different protocols, standard kind of RPC. LPC is the low-level internal single processor, single system version of it. We have the registry. Now, the reason the registry is particularly important, there's a lot of history in the registry, and I won't get into all that, But because we keep so much configuration state in the system, we need to have persistent state across when the system reboots. And I'll explain a little bit about the file system structure of NT, which is that if you look at Unix, Unix has the root of the file system is on a file system. It's the root directory of a file system. So this is slash. In NT, the root is the object manager. And we have to use a backslash. The object manager, underneath it, it actually has all the namespaces mounted. It has a registry, but it also has devices, and which can include things like a partition on a disk. And this is how you actually get a file system implemented. Now, so this is NT, object manager, whereas we'll go back up to Unix for a minute. What Unix has is it has a slash devices, which hangs off the root, and then creates a whole bunch of links and encodings which describe your system. And different systems in Unix do different things in terms of how you reconfigure and do that. In the NT system, we're trying to generate all this stuff basically so we can implement plug and play and create that kind of experience. You just plug something in, the system recognizes it, loads the drivers, and works. And so we need to be able to keep some state in the object manager's namespace, but the object manager namespace is constructed every time the system boots. Some of the information you need to persist because you learned something previously about what exact driver you should use and things like that. That state we have to keep in the registry. So in the way the system is configured, we need to have at least some part of the registry available in the operating system kernel itself so that we can run the system. And in fact, when the system boots up, we load the kernel, as you would expect, and the HAL, which is actually a separate file because we have multiple HALs that might work depending on your hardware configuration. And then we load the boot drivers. Actually load these, I think, last. These are the drivers you need when the system comes up before you can do anything. So, for example, you have to be able to talk to a file system, you have to be able to talk to the volume, you have to be able to talk to the controller for that volume, the IDE, the PCI, whatever. Those are the boot drivers. We load them into memory before we start executing the kernel, but we also load the part of the registry called the system hive. In fact, this is where we got the information about what boot drivers we needed to load. Okay, information like that. So this is the key information we need in the registry as we come up and configure the system. Okay. I will probably come up with another 1 or 2 boxes in a minute. You want to hit forward on that? There we go. The next one. This one? The next one. The last picture. Yes. Yes, something very important. So I'll draw over here, which is processes and threads. And looking at my cheat sheet there, there's a lot more information about the file system and the cache manager, which I'll draw in a separate picture. So we talked about the registry, and particularly how it's important kernel mode. LPC is just a communication protocol to allow you to invoke procedures in different processes. I want to talk more about the object manager. The object manager is one of the very special things about NT, which I really, really appreciate. It's a significant difference with Unix. I'd like to illustrate in a couple of points. I've already mentioned the stuff about how it's the root of the namespace, and file systems are actually mounted underneath the object manager rather than the file system itself being the root of the namespace. And there are a lot of reasons why I think this is more convenient in terms of how the system operates. But where the object manager really shines is in its unification of data structures and referencing of data structures within the system. So the object manager manages...
We only have a couple more minutes about it.
Okay. Manages objects. And the particular things we want to manage about objects in the NT system is we want to manage the reference counts I mentioned before. We like to have a standard way that we can update the reference counts so we can cause when the last reference count goes away, the object should disappear from the system. So we have a lot of stuff related to reference counts. We have something else, which is a whole class of objects, has something called a dispatcher header. Dispatcher header is the same thing we use for something called an event. It's a synchronization mechanism within the system. If you have a thread can wait on an event. And the event gets signaled, the thread says, oh, it happened. And so we have something that's like the select statement in Unix a little bit, in Berkeley Unix, that you can wait on multiple events. And you can actually, it's more flexible in this system. Here's the nice unification about the object manager. In Unix, I can wait on a select statement, usually on file descriptors, mostly which have to do with networking, or some versions of Unix with asynchronous I/O. Here, I can wait on synchronization primitives that actually involve other threads, things like events, semaphores, mutexes of various kinds. I can wait on I/O completion to occur, that when I/O is available in a file object, and this also networking. I can do something that Unix requires separate system calls. I can wait for threads or processes to have events or to terminate. I can wait on exceptions to signal LPC is available. There's a whole set of things that I can wait on. They're all unified through the object manager. And so this is one of the great unifications that occurs in NT that allows the implementation of the system to be clear, simpler, and provide a standard set of unified mechanisms. I'll add one more box here before we end, which is we have implemented security as a first-class entity in the system, which is just a very rich set of operations, security operations, such as the access control list. But because of the nature of the object manager, they work not just on files, but they work on any object in the system, including the events and the semaphores and all these things. And the other thing is that any of these things in the object manager you can reference with a handle. And this is the other generalization. And then handles, which you have in Unix, these small numbers, they call them file descriptors, you can duplicate across processes. You can share memory using handles. You can share events, other kinds of synchronization primitives, communication ports are a little bit trickier, but you can do all these things because the handle mechanism and the object manager mechanism is so incredibly general. And this is, when I understood this about NT versus Unix, I really, really started to like this system.
Fantastic. Well, it's been a great introduction, a deep introduction to the system. Thank you very much.